Next, let's talk about some practical applications of neural shading. I'll start with neural texture compression. Let's go back to the section of this course where we were training an MLP to reconstruct an image. The best result that we could achieve back then, before the introduction of latent textures, looked like the picture on the right, which looks similar to the original image but still visibly worse. The architecture of the neural network solution that led to this result is shown on the left. We take the texture coordinates in the UV space and compute some sines and cosines from the U and V inputs at different scales. This is called positional encoding or frequency encoding, and it helped us get a much better result than when the MLP was fed with raw U and V values. But we can still make it better. One option would be to make the MLP bigger, increase the number and size of the hidden layers. That will improve the output quality, but it comes at a significant computation cost. In the limit case, if we keep increasing the number of positional encoding bands and the size of the MLP, we'll get a discrete Fourier transform, which is great, but not the most efficient solution out there. A better option is to introduce another input to the MLP, called the latent textures. It's just one or several textures that are smaller than the original image by a factor of 2 or 4, with low precision, such as 2 or 4 bits per component. The latent textures are sampled at the same UV position that we're reconstructing, and the sampling result is fed into the MLP, along with the positional encoding. And the positional encoding is adjusted to represent the position relative to the latent texel, not globally in the image. This way, we're using the MLP not as a full image decoder, but as a transcoder from one signal domain to another, and it can produce much cleaner results this way, as you can see on the right. Using this approach lets us create a robust texture encoding solution with some important features. First, using a variable number of latent textures with low bit depth gives us a wide range of encoding bit rates. We found that the practical range for these bit rates is approximately half a bit per pixel to 20 bits per pixel. And these are pixels that can store up to 16 channels, not just 4, which is useful to encode complete PBR materials in one neural container. Most of the storage is used for the latent textures, and only a tiny fraction of the compressed texture size is used for the MLP weights, which are independent from the texture resolution. Second, the design where the network decodes a single pixel based on its UV coordinates implies that each pixel can be decoded independently. This means that we can use such a solution to sample neural textures directly in the shaders that normally sample material textures, such as G-buffer fill or ray tracing passes, and avoid decoding the textures into a traditional GPU-compatible format on load, although that is also an option. And finally, since the image decoding model is just a small MLP that is trained from scratch for every texture or material, there are no possible hallucinations like you might expect from large image generation models. Yes, at lower bit depths the image may be visibly different from the input, but the difference is just loss of detail and blur, not extra fingers. And speaking of image quality, perhaps the most important comparison that we can make for a real-time image compression solution is against the regular block compression formats, such as BC1 or BC7. Those are the two most frequently used formats for regular color textures on the GPU. There are other formats, of course, such as BC4 for single-channel images or BC6 for HDR images, and the ASTC family, but they have limited usability and somewhat similar characteristics. Generally, neural texture compression delivers much higher quality than both BC1 and BC7 at similar compression rates, or much better compression at similar quality levels. Here I'm showing some example materials numbered 1 through 5, with 1 being the most complex one with the lowest PSNR values, and 5 being the easiest one with a lot of mostly flat space. See how the BC1 and BC7 points are to the right and bottom of the NTC quality curves, meaning that NTC has higher quality or better compression or both. And the gap is wider for the more complex materials, indicating that NTC can be good at working with detail. Also, NTC compression artifacts have different quality from BC artifacts. NTC introduces blur and loss of detail, while BC introduces blockiness. Arguably, blur is less distracting. Another interesting feature of this plot is that NTC image reconstruction quality is mostly monotonic with respect to the bitrate. This means that even though the latent configurations for adjacent BPP values can be significantly different, the training process finds a way to use the bits efficiently. Finally, it's important to note that NTC works better not just for complex materials, but also for materials that have correlated channels. For example, when you have a PBR material with typical channels like base color, roughness, and normals, NTC works better when detail in the roughness and normal channels corresponds to some detail in the base color channels. If that's not the case, such as when there is a flat sign with some text on it, the detail from the text in the color channel might leak into the roughness and normal channels. This can be fixed by using a higher bitrate. Now let's take a look at the training process for NTC. Considering the rest of this course, you probably already have a pretty good idea about how a model like this can be trained, but let's do it anyway. First, on a given training step, we pick a random subset of pixels in the image that will be trained on this step. We could use the entire image, but that is less efficient. Typically, about 64,000 pixels is a good training set for one step. The pixels should be evenly distributed in the image, but we are organizing them into small tiles to improve performance. Then, for each pixel in the selected set, we run the decoder network as normal. We sample the latent textures and get feature vectors from them. They are concatenated with positional encoding to form the MLP input vector. Then we evaluate the MLP once for each pixel and get predicted colors or contents of other texture channels. At first, they are going to be way off, but that's okay. Once we have the predicted colors, we sample the input textures and compute the L2 loss between the reference colors and the predicted ones. The gradient of this loss is just a difference between the color values. That gradient is backpropagated through the MLP and accumulated to adjust the MLP weights. Then the latent texture sampling process is differentiated to compute the gradients for all latent texels affecting the output, and these gradients are also accumulated. The sampling, forward evaluation, and gradient backpropagation passes are done in one kernel. This is in contrast with established deep learning frameworks like PyTorch. They perform each step separately, dumping intermediate results into GPU memory. Combining everything into one kernel and applying some low-level optimizations improves training performance by 2 orders of magnitude. Finally, when the sampling and gradient accumulation pass is done, we run the optimizer to adjust the latents and MLP weights and go back to the beginning for the next step. Typically, 1 to 200,000 steps are enough to get a good result, and that takes about 30 seconds on a high-end GPU. So we have covered the basics and the training process for NTC. How can it be actually used in a game or another real-time renderer? The first mode of operation is called inference+sample. This is the original mode that NTC was designed for. We go through the shaders that perform material evaluation, such as a G-buffer or forward pass, or hit shaders in a path tracer, and replace the sampling of regular material textures with NTC decoding. Since the NTC decoder cannot filter the texture and can only return one texel at a time, we need to get creative with filtering. We usually don't want to use the nearest neighbor sampling, and we don't want to do NTC decoding multiple times per pixel to perform trilinear filtering. That would be too expensive. Instead, we apply stochastic texture filtering. Instead of loading all texels that participate in the filter operation and blending them together, we randomly pick one of those texels using a specially crafted PDF. On average and over time, such samples integrate into the correctly filtered texture. On the right of the slides, I'm showing a few important papers on the topic of stochastic texture filtering. The benefit of inference+sample is obvious. We get much lower video memory usage for textures than with BC. But the drawbacks are also significant. The on-sample decoding makes shaders slower, which can have a dramatic effect on the more complicated renderers such as path tracers, and you have to use STF that introduces noise. Although there are newer techniques like collaborative texture filtering that significantly reduce that noise. The second mode of operation is called inference+load. Here, we decode all textures for a material entirely during material load time. This can be done when loading the map in a game or when streaming in some model. But using raw uncompressed textures wouldn't be very practical, so we can encode these textures into BC formats compatible with hardware sampling and filtering on the GPU. The encoding process can be implemented very efficiently. The benefits of inference+load are that it's easy to integrate. There are no shader changes needed, only decoding and encoding at material load time. And it doesn't affect rendering performance because at render time, the GPU uses regular BC textures. The drawbacks are that we forfeit the video memory savings and only get the savings in on disk storage and download traffic, although that can be quite significant. Inference on feedback is what we call the integration of NTC into a virtual texturing system. In such a system, textures are subdivided into tiles, and the tiles are stored either in a hardware-managed sparse texture resource or in a larger texture atlas with software addressing. Every frame tracks which tiles are needed for rendering using sampler feedback or other solutions. We can fill these tiles by transcoding them from an NTC texture set into BC instead of loading them from disk. This mode combines the memory savings and performance benefits of inference on sample and on load, although less efficiently. We need to keep both the NTC and BC texture data in video memory, which limits the memory savings, and we need to track the tiles during rendering, which has a cost. Here is a quick quantitative comparison of the three NTC modes of operation. I'm using the Intel sponsor scene with curtains here and all materials converted to NTC. The on-load version is the fastest, but it consumes the most video memory. The on-sample version is the opposite, slowest but uses the least memory. And the on-feedback version is a compromise between the two. Finally, I'd like to summarize the benefits of neural texture compression compared to traditional texture compression methods. The obvious practical benefits are that it saves disk space and download traffic, and maybe video memory, depending on the integration model. It can be used on platforms with different hardware capabilities, using inference on sample on high-end hardware that supports it, and transcoding entire textures or tiles on load on hardware that does not. So you don't have to ship a game with two sets of textures for different platforms. And you can already get the SDK and experiment with it, it's available on GitHub. Conceptually, using neural compression allows you to use higher detail textures. If you keep the memory budget constant, better compression means that you can increase the texture resolution. The current architecture of NTC is flexible enough to allow different optimization techniques during compression, such as using perceptual loss function instead of regular L2 loss. This is more complicated to implement and slower to train, but allows for higher visual detail at the same compression rate. We have already seen some variations on the topic of neural compression from other companies. Some of them take the idea of neural texture compression and extend it to use BC to store latents, or to produce BC endpoints and not just colors. Some apply neural compression to grids of light probes to have global illumination maps baked for different times of day or different states of the environment, and not take up huge amounts of storage. Some of these solutions even work on mobile platforms. So maybe you can find some new application for small neural networks in real-time rendering? Give it a try.